Hey everyone, welcome back. In this video, we will be talking about how to implement the Anova and interaction plot for a randomized complete block design, specifically for our two examples, the insecticide and highway paint data, using R. So first thing first is we need to bring R up, which we did. The first example we'll be talking about today is the insecticide example. And so let's just recall what that example entailed. We have 3 treatments, which are the 3 insecticides. We have 4 plots, or blocks in this case, right here, here, and here. And again, our goal is to see if there's a difference between the 3 insecticide treatments. The first thing that I want to show you guys is how to make the interaction plot, which is shown in lesson B here, or more specifically right here. So let's see how we can do that in R first. So we got to read in our data. First of all, you always want to make sure that you're in the right directory. How you can do that is get working directory. Boom, I am in my correct directory. So we're going to run our data. It's always good practice to view it, make sure it loads in the way you expect it to. Because our treatment and plots are numbers, you just want to check the class. It's an integer, so let's convert that to a factor. Same thing for the plots. Now, what this code right here is going to do, so if we view our insect data again, notice how we have treatment, plots, and end seeds. That's the number of seedlings. What this is going to do right here is going to create a treatment mean and a block mean variable. So if I ran that, and now we view, actually should be able to just click that. Perfect. There's a bunch of NAs here. What we're going to do is we're going to fill these NAs with the treatment mean with respect to that treatment. So here to here is going to have the treatment mean for treatment 1. Here to here is going to have treatment mean for treatment 2. Over here we'll have the treatment means per block, and I'll show you the code for it. For those of you guys that are new to R, this code right here is going to find the indexes of the treatment that equal 1. So let's look at this. So 1, 2, 3, 4. The index of the treatments that have 1 are 1, 2, 3, 4. Just to give us a better example, let's say we want to find the index in this data frame where treatment is equal to 3. Run it and we get 9 through 12. 9 through 12. Okay, so this is going to get us an index. And then what we're going to do next is use that index to collect all the associated responses. So here's the index again, and it's inside the brackets. So this is going to pull out the responses corresponding to treatment 1. So we have 56, 48, 66, 62. If we go back here, what it's doing is it's going to these 4 rows and it's pulling out these numbers right here. Okay. Again, I'll change the numbers. So we're going to be pulling the responses associated with treatment 3. 80, 72, 83, 85. And again, we see that right here. Okay. So now what we're going to do is we're going to go into a for loop for the treatments to find the treatment means. So this is just a for loop, and what it's going to do is it's going to collect our index for the T treatment. It's going to for loop 1, 2, 3. It's then going to get the responses with respect to these index and take the mean. Then what this is doing right here is it's going to store the treatment mean that we calculated into the respective indexes for that treatment. Control copy, paste. So we look at our data. We now have the treatment means for treatment 1. we have the treatment means for treatment 2, and we have the treatment means for treatment 3. Okay? We're going to do a similar thing for looping over the blocks to find the block means. We had 4 blocks or 4 plots. So again, we're going to find the indexes related to block B in a for loop. This will loop 1, 2, 3, 4. Given those indexes, we're going to collect the responses with respect to whatever B block. We're going to find that mean, store it into block means, and then take that block means and store it into the respective. So let me take this one slow. So B equals 1. Let's just say this is how the for loop works. B equals 1. We're going to collect our indexes. Index block 1, 5, and 9. So that's saying 1, 5, and 9 are all in block 1, or plot 1. That's true. Now we're going to get the responses. That's what that does. Mean is going to calculate the average of those 3 responses. So block means, and then this last section is going to say, hey, let's put this block mean into 1, 5, and 9. We look at our insect data, and that's exactly what we see. Now, for loop's going to say B equals 2 and repeat the process. I will not be doing that, so boom. You look at the data, here it is. Then we're going to have to calculate our overall mean, which is just taking all the data and taking the average. Now, why are we doing this? Again, for the interaction plot, we want to do the estimated cell means, not the responses, but the estimated cell means. Okay, now what this line of code's doing is, if we go back here, it's going to take our treatment means plus our treatment means plus our block means. So add across here, and then it will subtract the overall mean to get our estimated means. So you'll see we'll have a vector of 12. Yes, 12. And then what this is doing is this is going to plot the interaction for us. So our x factor is going to represent our treatment on the x-axis. Our trace factor is the block, so this is going to be the different lines. And then our response is going to be the estimated cell means. And boom, make this a little bit bigger. These colors associate to the same colors that we saw over here. Fantastic. Now that we have our interaction plot, we see that it looks additive because they're parallel lines. Let's move over to the Anova table. So for this Anova table, for this line of code, it should look very familiar to what we saw with the completely randomized designs. But now we have treatment and we have plot. And a good way to think about this, and why we like to use the statistical models, is originally, if we go back here, we have our response, we have our mu, we have our alpha I, we have our beta j, and we have our epsilon. Okay. Here we have our y, ij's. We don't need to input the mu. R can do that itself. We have our treatment effect, we have our block effect, and then we don't have to put in that error. And so this right here is really following this, where we don't have to put this in because R can do that itself, and we don't have to do this because R can do it itself as well. And so we're really just adding in these 2 effects. And so run these 2 lines and we get our ANOVA. And again, remember, here's what I was talking about, where we have treatment and we have plot. These 2 terms are going to depend on what these 2 terms are up here. Again, R and Jump and any other software will output these F and P values because we didn't tell it what is a treatment and what is a block. And so we have to be smarter than the computer And know not to use these. Bad. F value and P value, because plot was our block variable. Okay? Now, you might be asking, how can I also do Tukey's and contrasts? It follows the same pattern. Here's your line for Tukey's. Again, remember, treatment is what we're wanting to compare. And so you always want to make sure that this matches up back to your variable. And you have to run this library, don't forget that. So Tukey's, you can look at the summary, and there you go. If you want contrasts, it's the same thing. Make sure your treatment is here. And then right here, I saw some people get confused during office hours, which is absolutely understandable. So these are going to be your contrast coefficients. And so maybe in this case, we are going to be looking at our contrast coefficient. C1 is equal to 1, C2 is equal to -2, or C2 is equal to -1, and C3 is equal to 0. And so what we'd be looking for here is, does the first treatment differ from the second? And these contrast coefficients come from your hypotheses test. Okay? Just show you that this runs and it works. Boom. So another example, just to run through at least the Anova part and the interaction. We had a second problem, which was the highway paint, where our goal was to compare the reflectivity. This was the old one, and where we had 4 treatments, 4 blocks because of location, and each location has 4 sections painted by the 4 paints. To run through this one real quick, we got to load the data. Again, always looking at your data is very helpful. You got to check the class. The paint's going to be a character. Why is that? Because paints, the variable starts with a P4, so it's going to make it a character, or it's not technically a factor, but it won't impact our results. Then location, which we're going to have to turn into a factor. Oh, mini error, copying, pasting. We might need to make sure that this is the paint data. So for the interaction plot, again, we need to calculate our estimated cell means. How we can do that is by first creating these 2 variables in paint that are NAs that we're going to come back and fill in. So this for loop here is going to fill in the treatment means with the respective paints. This right here is going to fill in the block means for the respective blocks. We're going to calculate the overall mean. We're going to calculate the estimated cell means, and then we're going to use this interaction plot to plot them. Ba-doom. Then for the Anova table, again, your Y, your treatment effect, your block effect, and voila. So this concludes our tutorial in respect to lesson 3, where we were talking about the interaction plot and the Anova for a randomized complete block design.